This week, we're going to be talking about the ethics of artificial intelligence. So just like with last 2 weeks where we talked about geoengineering and genetic engineering before that, we're really kind of out on the edge of the unknown here. So we're dealing with technologies that we don't yet fully understand. We don't know how they're going to develop. We don't really know for sure what the risks and benefits are going to be. But nonetheless, AI technology is advancing rapidly right now. And its place in our lives is expanding at an incredible rate. So I think this is a really important topic for us to do at least a little bit of thinking about. So I'm going to start this video by just talking a little bit about how modern AI functions. And for the most part, the crunchy details of programming and artificial intelligence are beside the point for us. But there are a couple of main sort of bullet points that I want you to get because they're important for understanding how the ethical issues that I'll talk about after this play out. So this video, a little bit about how modern AI works and a couple of kind of ethical questions that arise from that structure. Okay, so I'd like to compare modern AI, the kind of stuff that's hot right now, with what some people have called good old-fashioned AI. I believe John Hausland coined that term. So good old-fashioned AI is AI as it existed from the invention of the electronic computer to about the 1980s, mid-1980s, something like that. Instructions would be written by hand. So they would hand code specific instructions for what to do under various circumstances. So those instructions would very often take the form of these conditional statements, an if-then statement. So if this circumstance comes up, then do this. Otherwise, do something else or do nothing. So if you're fighting enemy in a video game from the 1990s, they very likely had a script like this. The script would say things like, if your hit points are low, use a healing potion. That kind of thing, right? So the behavioral responses that look intelligent to us would be hard-coded and coded by hand. So somebody had to kind of go through all of the circumstances that it was probably going to encounter and write a rule for what to do in that circumstance. So the disadvantage of this way of doing it is, of course, that the computer is rarely going to do intelligent things that you didn't sort of provide to it. You really have to, all of the intelligence comes from the programmer using their intelligence and judgment about how to behave and just telling the computer very specifically how it's supposed to behave. It's generalizing very broadly here, but in the good old-fashioned AI era, the computer rarely was smarter than the programmer at a given task. You could impart intelligence onto a computer, but it didn't really generate intelligence itself in any meaningful sense. That's a little too broad, and the good old-fashioned AI era kind of smoothly transitions into the era that we're in now. So it's not the case that, hand coding conditional statements has gone away. That's definitely a part of modern AI. But there's another structure that's become really, really central, and that's what I'd like to talk about now, which is neural networks. So neural networks are a very different way of generating artificial intelligence. And for much of they have a long history. They have a history that's almost as long as the electronic computer itself. But for most of from the 1940s until the 80s, something like that, they were more an object of pure scientific research rather than a practical tool that people used in all kinds of applications. But in the mid-1990s, there were some really big breakthroughs in the design of neural networks, including the things like the wake-sleep algorithm by University of Toronto's own Geoffrey Hinton. So people got much smarter about how they were designing these things, and those improvements in neural network design combined with vast improvements in the processing power available, combined with massive increases in the amount of data available to feed to the neural networks. I'll talk about that in a minute. All come together to make these an incredibly powerful architecture. And when you hear stuff about machine learning or deep neural networks, all of that is referring to this basic architecture, of which there are many, many variations, and I'm just going to go through the simplest one because I think that's going to be enough for us to get what's going on in the ethical questions that are going to come. Okay, so for our purposes, again, I'm going to explain like the 1980s version of this, maybe even the 1970s version of this. So a really, really simple example, but it's got all the main elements that I think I need to explain what's going on with modern AI in terms of ethics. So when you're trying to use a neural network, what you've got is a bunch of nodes, these little circles in the image beside me, and those nodes are connected by little connections that have weights. Suppose you're trying to train a neural network to do a certain task. Classification tasks are a really standard one. So you want to train up a neural network to do, decode handwriting. Let's say this one, we just want it to be able to distinguish the numbers, 1, 2, 3, 4, right? So you give it an image and you want it to be able to tell you which number is in that image. So suppose that's our goal. So the nodes of the network are all connected up. There's one layer of nodes called the input layer, and you feed information into the input layer. So let's say the thing that we're trying to represent is a number. It's just a set of black and white pixels. So the input layer gets like ones and zeros, 1 for black and 0 for white. Let's suppose. So that's the far in this image here. That's the far left layer gets a bunch of ones and zeros. Now those input nodes pass their activation onto deeper layers of the network, and they pass them through those connections. Now those connections can be weighted, which means if you get this node gets a 1 because there's a black pixel there. The weight of the connection adjusts the value that it passes to the next node. So it could be like the next node, if the input node gets a 1, the next node could get a 3 or a -2 or whatever. This kind of has a similarity to the structure of our own brains and how our neurons are connected. So when one of your neurons fires, it fires a chemical signal down the dendrite, I think. And that chemical signal can either increase the activation of other neurons it's connected to or decrease it. So it can either excite or inhibit the activity of nearby neurons. So there are some rough similarities between this and how our brain is organized. So to train a neural network, so that's the kind of basic structure of a neural network. Now you have to train it. So you got these nodes all laid out and connections between them. You want to teach it to do a thing, right? You want to train it up to do a categorization task. So suppose we're trying to get this, we're feeding it this pixelated image of the number 9, and we're trying to get it to categorize it as a 9 rather than an 8 or a 7 or whatever. So when you start training a neural network, usually the connection weights of the nodes are randomized. You just set them to whatever, and then you feed it some data, and it'll make a guess at what it's seeing. So it'll assign probabilities in this case to, how likely do I think this is a 1? Say it's 10%. How likely is this a 2? 14%, whatever it is. And then you can quantify how wrong it was. So the most simple algorithm for training up a neural network is what's called the backpropagation of error. So the first time you feed data into an untrained neural network, it's going to make a wild guess. It's going to be really, really wrong. But then you can use that guess to quantify how wrong it is. And then there are quite sophisticated statistical techniques for, with the quantification of how wrong it was, adjust the weights of the connections. You tune those weights to make it likely to be less wrong next time. Right? So you make a change to the weights that causes it to be less likely to make that same error or to make a smaller error. So you do this over and over, feed it some data, quantify how wrong it got it, and then, because you know the answer, this is a 9, and so it says, I think that's 14% likely to be a 9. You know that it's off by 86%. And then you use this technique to tweak the weights to lower that to 80%. And then you do this over and over and over again with new data until the weights slowly converge on something that can do, hopefully, an adequate job of the categorization task that you're working with. Okay, so all of that was to get us to the point where you have something of a picture of what a trained neural network looks like. And what a trained neural network looks like is a set of nodes with connections, and those connections have weights. Those weights have been established by this repeated training. And again, the simplest way of training it is backpropagation of error, which I just described to you. So the important part for us, the part that I really want you to appreciate, is that the programming is in some sense entirely encoded in those weights. And in modern neural networks, I mean, this one it's got 3 layers and a handful of nodes in each layer, but modern neural networks can be much, much more complex than this. They can have millions, billions of tunable parameters, different things that can be tuned up during the training process. So a modern neural network, it's got, let's say, 1 billion parameters, and its ability to do the task assigned to it is entirely encoded in the way those parameters are tuned. And those parameters have dense interconnections with each other, right? So the parameters have, like, what it does is a result of 1 billion parameters all densely interconnected in their effect on each other. So what that means is it's really hard to figure out how a neural network in some sense does what it does. Now, of course, we understand in some broad sense how it does what it does. People design them, and they have to do that very carefully to get them to work. But the actual details of how it makes the specific judgments it's been trained to make are, generally speaking, very unclear, hard to reconstruct. And the actual answer to, like, how did it do this? Say, well, these billion parameters had this number, and when you feed this specific data into those billion parameters, this is what comes out. And that's the actual answer. There might not be a simpler, cleaner, more intuitive answer than that. Now, compare that to the good old-fashioned AI where there was a little subroutine that said, when your hit points are low, use a potion or whatever, right? So there was actual, like, clear, legible, understandable, line-by-line instructions that a human being could understand. With these things, the magic happens in some sense beyond our ability to clearly comprehend. Not completely, but there are techniques for, in some sense, reconstructing what a neural net is doing. And some neural nets are specifically designed to be easier to interpret than others. But by and large, most modern neural networks are very opaque. Their operations are very unclear. And that all matters because we are in many ways putting our lives in the hands of these artificial intelligences. We depend on them for a great many aspects of our life, and we don't really know how they do what they do in the sense of the specific algorithm and how its parameters are tuned. There is some conversation and movement towards requiring that the process by which a neural network works should be interpretable. Europe is enacting some legislation right now in that direction, but I'm not sure they're going to be able to get that because these things are just really, really hard to understand. And their operations don't correspond to clear, intuitive human concepts. What we know is data go in and then answers come out, and we can evaluate how good the answers are, but it's really tough to get inside the inner workings of these things. It's just too much information for us to process. So the fact that we don't have easy access to the inner workings has sometimes been a problem. So here's a classic story from, like, way back in the history of neural networks. This is from the earliest generation of neural networks. And this is a quote from an interview with Marvin Minsky, one of the kind of pioneers of AI. Minsky says about one of these perceptrons. It was looking at a scene of a forest in which there were camouflage tanks in one picture and no camouflage tanks in the other. The perceptron was developed for, like, military use primarily. And the perceptron, after a little training, made 100% correct distinction between these two different sets of photographs. That's pretty good, right? Then they were embarrassed a few hours later to discover that 2 of the rolls of film had been developed differently. And so these pictures were just a little darker than all the other pictures, and the perceptron was just measuring the total amount of light in the scene. But it was a very clever of the perceptron to find some way of making the distinction. So its task is to distinguish between tank and no tank, but all of the tank pictures they collected were slightly darker than all of the non-tank. And, it was getting the right answer, but for the completely wrong reason. So the inner workings really matter quite a lot. This is a very old story. This kind of thing is carefully guarded against these days, although it's not an easy problem to completely eliminate. It remains a problem, although people have much more advanced strategies than they did back then. Okay, so a more recent example of this that fortunately nobody got hurt in this. Don't worry, this story has a reasonably happy ending. But in the 1990s, a PhD student called Rich Karuna was working on a neural network to do medical triage. Like triage is, of course, when you go to the hospital, they look at you and sometimes, if you go to the hospital and they say, take a seat, we'll be with you when we can, that's actually a good sign. If they say immediately, oh my God, get that guy into the back right away, you're in trouble, right? So triage is the decision of how quickly and how much medical intervention somebody should get. They're working with limited resources, of course, so they have to sort of allocate those resources smartly to the people who need it the most, the soonest. So that's triage. And Rich Karuna was working on a neural network, trying to train it up to do this sort of categorization task. What level of triage does this particular patient need? So the idea was to enter a few data points about the person and hopefully be able to kind of correlate those data points with clinical outcomes, so how well did the patient do, in order to decide who needs the most urgent care. The idea being, if you got bad clinical outcomes, you sort of rise up in the triage sort of ranking system. You get more care quicker. They got a version of this up and running, and somebody suggested that they actually should try this in a real hospital. This was all theoretical at this point. Somebody said, we should try this in a hospital. And Rich Karuna said, I really don't think that's a good idea because of precisely this opacity thing that I've been talking about this whole lecture so far, which is we don't know how these things work. We don't know what it's doing. And it's a really good thing that he said that, because a colleague of this guy noticed something about the data that they were working with. The data that they were working with had some correlations that would have thrown off its decision-making process. Specifically, there was slightly better outcome. So with pneumonia, so you get pneumonia, where do you go on the triage? Well, it depends on other factors about you. They would enter things like your age and your overall health history, that kind of thing. So people who had caught pneumonia, really quite scary lung disease, and had asthma, right? Those people, in the data that they were training this neural network with, those people actually had slightly better outcomes than people who didn't have asthma. So if they just sort of handed this thing a bunch of training data and said, okay, tell me who's got the worst outcomes, they get the most care, it would have given less care to people with a pre-existing lung condition who had then caught pneumonia. The reason why those people had, in the historical data that we're using, slightly better outcomes is because doctors and nurses very correctly said, oh my God, you've got pneumonia and asthma? You need a lot of help. So they would give them the most and the quickest care available, because it's super deadly to people who have both of those conditions. That's a really dangerous combination. So the reason people with asthma had better outcomes when they got pneumonia is because they were shot to the top of the triage hierarchy and given urgent care. So there was a correlation between doing better and having asthma, but it wasn't because they had asthma. It wasn't that having asthma made them better off. It made them worse off, but they got more urgent care because doctors knew, they understood the situation. They weren't just sifting through data for correlations, which is all a neural network can really do. It can sift through data for correlations. The doctors understood the mechanics of this thing. They understood what pneumonia is and what asthma is and how those things combine. That's why that correlation exists. It wasn't that having asthma was causing your outcomes to be better when you have pneumonia. So, yeah. Okay, so with that kind of problem in mind, let's think about another set of cases. There's a bunch of similar cases similar to this, but I'll focus in on one kind of AI use in the justice system. So one of the most controversial uses of artificial intelligence, this is one that's been sort of discussed widely, is use in criminal risk assessment. So when you're maybe trying to get bail, or when you're applying for early release or some kind of release on probation, something like that, usually it's a panel of people who sit there and go through your case history and decide how likely it is that you are to reoffend. And if you're very likely to reoffend, they were less likely to let you out, or they're more likely to sort of put heavier restrictions on you, some stuff like that. So in a bunch of different places in the world, the justice system is, and in the U.S. is a particularly prominent case here, the justice system is kind of straining under the administrative burden of all the people that they put in jail. So they're looking for ways to make the process more efficient. And they thought, aha, artificial intelligence. It can give us a recommendation. We'll feed in a bunch of data about the prisoners, and it'll give us a recommendation of how likely it thinks they are to reoffend. So they train those neural networks with historical data, right? So they take a bunch of histories of people that have been arrested and released and whether they were rearrested. They train it up, and then once it's trained, they feed it a current case and say, okay, make me a prediction about how likely you think this person is to reoffend. But just like with the pneumonia and the asthma, just like with the tanks and the no tanks, these algorithms don't detect causal relationships. They don't detect what's making what happen. All they detect is correlations, things being related to each other, and things like your socioeconomic status or being from a certain neighborhood. They feed in like where your family lives, what your family circumstances are. They feed in a bunch of information that, if it was me undergoing this scrutiny, I would not want the neighborhood that I live in to be part of the decision-making process for whether I'm more likely to offend. This is a kind of bizarre group punishment on whole groups of people for being from the wrong part of town. Literally being from the wrong part of town can give you more likely to reoffend score. And that's just bizarre collective punishment that seems to a great many people, a great many human rights activists consider this quite unjust. And just more generally, correlations just don't add up to causation. And once again, all that these things can do is tease out correlations. So here's a fantastic website called Spurious Correlations. Here is a reasonably robust correlation between letters in the winning word of Scripps National Spelling Bees and the number of people killed by venomous spiders. And those two things just happen to correlate. And if you were giving a bunch of data to a neural network, it would detect that correlation and be like, these two things are related. They are related in the sense that those numbers track each other with some degree of robustness, but they're not related in the sense that one thing has anything to do with the other thing. So that kind of stuff just crops up all the time in the world, and these neural networks are unable to do the kind of common sense reasoning that humans can to make those decisions. Okay, so in the next video, I'm going to continue on with this idea of biased algorithms. So there's a really big discussion about bias in algorithms. I'll continue on with that discussion and then move on to some other issues in the kind of broad area of the ethics of AI.